In any case, we had plenty of information from last lecture where we considered the sign of f prime of x. And if we remember, we had an interval where if I consider the sign, here it was positive, here it was negative. I had the 0 of f prime around here. So if I follow the interpretation that the positive sign of the derivative means that the function is increasing, and here I would have that the function is decreasing, well, we had our critical point here. Here the function is increasing, here the function is decreasing. So therefore, you have at 0 a local maximum, the value is 0.4. Right? So that is where we left. Then we also have the sign of the second derivative. So if I were to consider the sign of f double prime of x, well, I had some possible inflection points at -1, 1. If I consider the sign of the second derivative, here f double prime was positive, here was negative, and here it was positive again. So if we want to do a little by little interpretation of the sign of f double prime, well, this means that in this region f prime grows. Here in this region f prime decreases. And here f prime increases again. So if you look at the concavity, you would have something like this. In this region is concave up, in this region is concave down, in this region is concave up again. So if you remember, f double prime of x is equal to x squared minus 1 e minus x squared over 2 divided by square root of 2 pi. So clearly, if you look at the sign analysis, what you would have is that basically, well, let me make a little space over here. F double prime of x is greater than 0 for regions where the absolute value of x is greater than 1. F double prime of x is less than 0 for regions where the absolute value of x is less than 1. So these are actually inflection points because you have the change of concavity. So the concavity changes at -1 from up to down, as you can see, concave up, concave down. And at the point x equal to 1, it changes from down to up. Okay? So that's why these two are inflection points. And the whole idea of this analysis is that we can use all the information that we get from f prime and f double prime in order to make an appropriate plot of the function. So, well, we know that these are inflection points, that is already said. And now what we will do is that we will use both sets of information so for the graph of the function e to the minus x squared over 2 divided by square root of 2 pi. And, well, first of all, you know that the exponential is always greater than 0. So the function is always positive, that you know. For all x. So another thing to consider is that if I consider the limit when the absolute value of x goes to infinity, meaning that I can either go to plus infinity or minus infinity of e minus x squared over 2, but that limit is 0. So basically I have an exponential decay if I go to plus infinity or minus infinity. That is what we know. So summarizing all the information that we saw at the end of last class, well, we have the following, right? So we know that the exponential function decays. We have the value of the function. We also have the points, which are inflection points, 1 and minus 1. Here you have a maximum, a local maximum. It decays to 0, and here you change the inflection. So if you were to draw your function, so this is y, this is x, this is the function, well, the normal distribution, e minus x squared over 2 divided by square root of 2 pi. This would be an inflection point, 1.24. This is the other inflection point, minus 1.24. The maximum value of the function is achieved at 0 with the value f of 0 equal to around 0.4. So if you have not seen this before, this is a normal distribution. It also has the name of a Gaussian distribution, standard or normal standard distribution, also Maxwellian if you were to work in physics, but it has very important applications in probability. So this function is very important in probability and statistics. If I were to name it, if you have not seen it before, but I'm pretty sure you have seen it. The name is the standard normal probability density function. Well, this is just PDF, probability density function is the standard name when you work in theory of probability, but the name is this part. Well, clearly what you have is a bell shape for this curve. That's why it's also called bell curve. Of course, the applications are in physics and social sciences. And there are many applications to it in this particular context where you can talk about, for example, distributions of IQ scores. So it's very probable that after the first midterm, if we draw a histogram of the grades of everybody in this group, we have 450 students. It is very possible that we will have a Gaussian distribution, actually. So that's one thing to mention. So another application is the measurements of large populations of living organisms. Of course, well, for the people who like physics or engineering, this distribution is actually pretty useful when you want to have the probability of a particle in a gas having a given velocity. So this is just for your math culture. The velocity of a molecule in a gas. So in any case, all what I'm trying to do is to make the point that this function is very useful and you should try to learn the properties. So this is the end of that example. We will continue with some other applications that involve the exponential and the logs. The next application is when we consider exponential growth and decay. So let's say that you have a quantity Q of t. So you have exponential growth when Q of t is of the form Q naught, remember our notation, e to the kt for k greater than 0. So Q naught is a constant, and then it's multiplied by the exponential, where you have kt and k is positive. On the other hand, it's possible that you might have an exponential decay if the function is of the form Q naught e minus kt, where k is greater than 0. So the change, of course, is that now the argument of the exponential has a minus sign. So, if you want to imagine it, just take a practical example, right? In the exponential growth, k equal to 1, of course, it's going to grow exponentially. In the other, you have Q naught e minus t, so of course you're going to have a decay. So at this point, you're familiar with this. So the applications are in business, economics, social sciences, etc. And to reinforce all what we have learned regarding the exponential function, well, we can draw the graph for these two cases, right? So let's say I have a QT plane. So this is the t-axis, the other is the q-axis. This is Q naught. And I have an exponential growth, right? So I have something like this, where the function is of the form Q naught e to the kt, where of course k is greater than 0, so that I have growth. So this corresponds to exponential growth. The quantity t usually has interpretation of time. That's why it's always greater or equal to 0. And for the case of exponential decay, if you remember when we did our plots, so this would be the initial value, Q naught, which happens when you plug in t equal to 0. This is the time axis, this is the q axis, and the function is of the form a constant, which is called Q naught, times the exponential of minus kt, where of course k is greater than 0, so that you have the decay. So this corresponds to an exponential decay. Well, information that we already know. As t approaches infinity for the exponential decay, this goes to 0. So that we know. The virtue of this analysis is a couple pieces of information, which is that at the time t equal to 0, the initial value of the function, if you have not seen this before, would be Q naught times the exponential of k times 0. This is 1 because we have the exponential of 0. So this is Q naught. So this Q naught constant, in the case of this particular function, takes the place of the initial value. And the second application, or the second important piece of information, is that perhaps this will be the first time that you will see a diffie Q. So just to give an example, if you have a function of exponential growth, let's say that you take the derivative, right? So when you take the derivative, the k constant comes down, then you have k naught, exponential of kt, which is equal to k times the original q. So if on the other hand, you were to make this same analysis for the exponential decay, then what you would have is basically q prime of t equal minus k q naught e minus kt. But if you remember, this is minus k q of t. So this we might bump with later in the course, but this is the first time, most probably, that you have seen a differential equation. It doesn't matter. It's just like if you were to do the computation of the relative growth, basically dividing Q prime over Q, you will have a constant K. So that's an important piece of information for exponential growth and exponential decay. Okay? In this case, what you would have in the first one is Q prime over Q equal to K. In the second case of exponential decline, so what you would have is Q prime over Q, this quotient equal to minus K. So this is an important property of exponential functions if you have not seen it before. But that is all that we will talk about. Now what we will do is actually a practical example with this piece of information, where considering example 4.4.4, we will find some exponential sales rate. So in this example, actually what we will have is some piece of information and we will try to fit an exponential. Loosely speaking, that is the idea. So the statement of the problem goes like this. So, look, of course it's stated in a longer way in the book. I'm just trying to give only the necessary piece of information to try to make it as short as possible. So, assuming the sales will decline exponentially at a company or a firm, and knowing that the sales level is 21,000 units at the initial time, and 5 weeks later, it is of 19,000 units. That's just the statement. There are two indications. So the first one is to find a couple constants, which we're going to call S naught and K, such that the following holds. That we have a function for the sales, which is a function of time, which is equal to the constant S naught times an exponential minus KT. So little by little, look. I have some information, like the owner of the company or the accountant has an info that there is a decline of sales, and he's expecting a decline that follows an exponential law. So we will be provided, actually we have been provided two pieces of information, because this is the amount of units at the initial time, and then this is the amount of units 5 weeks later. So there is also a coupled piece of info, because the unit of time in this case is weeks, if you want to stick for t equal to 5, and then, I mean, this is also in terms of 1,000 units, so that is useful. So find the constants such that you have this exponential decline model, and that it gives the sales level t weeks after the initial time. So if you think about it, what I'm going to do is to fit two parameters that define the exponential decline to 2 points. That's all what I'm going to do, is to do an exponential fit. Okay? So then there is another question. What is the sales level 8 weeks after? Second? Yeah. Okay. So the second indication is at what rate should the firm expect sales to be changing T weeks after, and then in the problem there is a phenomena that makes the declines of sales, which is that they stop the advertisement, okay? So after the advertising ends, it's a long problem, I know. But I mean, if I were to state the whole stuff, we will even take longer. So there is an end of an advertisement that causes a decline in the sales, to which we will make a fit. And then we're also asked what is the percentage rate of change. So this is just a rate of change expressed as a percentage, that's all. So try to review the statement. The first one is basically to say that we will do an exponential fit. In terms of the actual solution of the problem, this is what we have. So we have the sales, which we will denote by the quantity S, in terms of a variable, which is the time. Well, but before that, we were going to indicate that the sales are expressed in thousands of units, just to keep it in mind. So, for the first indication, we know that at the initial time, in the units that I have chosen, meaning that weeks for time, thousands of units for the sales, what I have is that the initial amount of sales is 21 in thousands. And then for the second point that I'm given, after 5 weeks, that's why t is equal to 5, so 5 weeks after the initial time, what I have is that S of 5 is equal to 19. Again, there is an indication that time is measured in weeks. Okay? So far so good? All right. So, just to be more explicit on the methodology, I will indicate that we will fit an exponential decay curve into our 2-point data, okay? So that you understand what is the procedure. So I have been given a function that I will try to fit with 2 parameters, S0 times E minus KT. And then if I do the substitution, on one hand I have plug in the initial time, t equal to 0, right? So that means that I have the constant S0. And on the other hand I have the value. So that means that this S0, this constant, is equal to 21, just by this first point. Do you guys see the procedure? Is it clear? I have been given an exponential decline law. I want to fit 2 parameters. The first point just gives me right away one of the constants. So the second one, I mean, and if I were to write even this, I mean, since I know that this happens, this is 21 E minus KT. Again, remember the units in which every quantity is measured. So the second piece of information is that after 5 weeks, the value of the sales go to 19,000 units. That's why we have 19. And then if it obeys this law, I would have 21 exponential of minus k times 5. Again, this k has its own units, in a way. It's inverse of weeks. So you have to be careful into that. But if I were to do the manipulation, I pass the 21 to the other side. So 19 over 21 is equal to e to minus 5k. If I apply a natural log to this, I would have minus 5k, because the exponential and the natural log are inverse functions. And then that would mean that k is equal to minus 1/5 multiplied by natural log of 19 over 21. So if I were to actually plug in my calculator these values, I would simply get that k, well, is around approximately 0.02. And now I have all the information, because this is the piece that I was missing, right? So in this case, I have s of t equal to 21 e minus 0.02 times t, where t is greater or equal to 0. Then I was asked what happens at t equal to 8, which I can just plug in now that I know the actual law. So I just did the same way you fit 2 points to a line. In this case, actually, somebody told me, do not fit a line. Fit an exponential decline curve. And I had to figure out the initial value constant and the rate of the exponential constant. That's all what I did. And I fitted 2 points. That's all. Okay? The first one was because of the initial value at the initial time. The second is just after 5 weeks. Now that I have the law, I plug in the value at 8 weeks. So I have s of 8 is equal to 21 exponential of minus 0.02 times 8, which is approximately 17.9 thousand. Of course, don't forget your units. 1,000 units. So that covers the first part of the exercise. The second part is asking me about the rate of change. So for the rate of change, we already know what to do. We simply compute s prime of t, which is in this case, okay, I had this model. So just applying my laws for exponentials, I have minus 0.02 times 21 e to minus 0.02 times t. And if I do the computation, this is around minus 0.42. Let me use the eraser because maybe it's not clear for you. Minus 0.42 exponential of minus 0.02t. But just do the multiplication of these two. So I was also asked to express the percentage rate of change. So this actually involves a definition. Where what you have will be denoted by PR, and it is, and I will explain it in 1 second, this is 100 times s prime of t over s of t. So this is the relative change, but because I'm going to express it in a percentage, I multiply by 100, okay? So here I would simply just plug in the values of this ratio, which in fact is pretty useful because, okay, I have the 100. Here I have this factor of minus 0.02 times s of t. This is because I had the exponential law. If you think about it, in this function, here is s of t, here is this factor. And then, because it's relative, I'm dividing by s of t, so I can do a cancellation. So if I follow the computation of PR, this is 100, and the only factor that survives is minus 0.02. So this is equal to minus 2. So this is actually 2%. So as a percentage is minus 2. So sales decline at a rate of 2% per week. So this is just a common convention. At the end of the day, you see that it is tied to the argument of the exponential, because that's the way this minus 0.02 came out when we took the derivative. And this is actually simply just to enforce the learning. This is k, which was approximately 0.02, simply expressed as a percentage. So, this problem is done with an intention, which is to tie this particular problem to a general knowledge. And the general knowledge is the following. That in general, if you have a quantity that follows an exponential law, where you have a constant, k0, times the exponential of RT, the percentage rate of change, following the definition that I just used, is PR times equal to 100 times Q prime divided by Q, if you want evaluated at the time t, because it depends on time. So think about it, right? When I have the derivative, simply the factor r will come back. So this is r, Q0 e to the RT, and Q0 is equal to Q0, Q of t is equal to Q0 e to the RT. So I will have a cancellation of these two terms, and this is only equal to 100r. Okay? So this is simply converting the r to a percentage. That's all what it's trying to say. And in fact, this percentage rate of change, it is clearly related to the coefficient that appears in the argument of the exponential. So just to say that this is the rate r expressed as a percentage. That's all. Let's see. Okay, yeah, this would be what I want to cover about this exam. There is one last application, which is related to the learning curve in psychology. Do we have any psychologists in this class? Some? Who is a psychologist? Okay, never mind. Well, there is a common expression, if you have not heard of it, which is called learning curve. When you are presented with a new problem and you have to figure out how to do it or to be trained. So, okay, the application in psychology, it is in your textbook. And this is a function of the following form. So you have a function q of t equal to b minus a e minus kt, where of course what we are assuming is that a, b, and k are positive constants. So, look again. All what we're trying to do is to exploit the power of exponential models. In general, this is, as somebody who has done a bachelor in physics and a PhD in mathematics, my 2 cents for advice for you regarding the exponential. Look, the exponential comes up when you deal with random processes. That's all. Okay? That's pretty much why it appears in all these phenomena. So, in any case, let's continue. So this is a function that I give in particular. It's the learning curve. So for t greater or equal to 0, this is a model for the relationship between efficiency of an individual performing a task and the amount of training time of experience of the learner. So, given the function that we've had before, which was over here, if I were to compute its derivative, so for the rate of change, let's do the computation. I have q prime of t equal to Ka, so this is an equality, Ka, E minus Kt. Now something to notice actually, well, so the minus goes because of this argument, is that this quantity is always positive, if you notice, because all the constants were assumed to be positive. Now, if I were to compute the second derivative, what I would have, so I have, okay, again, this factor minus k, so I would have minus k squared, a, e minus kt, which is in this case negative, right? So, okay, this is important because if the derivative is positive, that means that the function is increasing. And if q double prime is less than 0, what you have is that the function is concave down. So q is concave down. So we simply, as all the previous examples, we want to gather as much information as possible from the function to be able to draw a plot. So if I were to consider the vertical intercept, meaning the intersection with the q-axis, that simply means that I will evaluate the function at 0, which would give me b minus a. Now, if I consider, because look, again, I have an exponential decline in the function, right? So, if I were to consider the limit as I approach plus infinity in time of the function, what I would have is b minus a, so the rules of the limits that you learned in high school, times the limit as t approaches infinity of e minus kt. The reason I'm doing this is because it's 0. And here I have simply, well, b minus a multiplying by 0, which would be just b. Okay? So this is just to say that q equal to b is a horizontal asymptote. Meaning that, okay, when we approach infinite time, essentially, we have a constant value for the function, which is b in this case. So now we have plenty of information to draw the plot. If I were to draw it, this would be y. So this is the initial value, which was b minus a. So this is at 0. This is time. Then there is a value to which you approach as time approaches infinity. And you have something like this. So you have exponential behavior and then whoop. So b has a name, which is very famous, the learning capacity. Well, because what it's measuring is basically the maximum efficiency that you will get when performing the skill, right? So t represents the time that you're trained to perform a skill, and the q is measuring your ability. So you will never go past b. That is essentially the point. The function, of course, it's q, which is b minus a e minus kt, which is called learning curve. Okay? So in this case, the function was pretty simple, so I was able to do a quick analysis, value of the function, limit, derivative, have all the information. Of course, I know that the function is concave down. The function is always increasing, which is why it has this shape. Second derivative is negative, that's why it's concave down. Both are being satisfied in this plot. I have an increasing function, which is concave down, which is approaching b, and which has the initial value of b minus a. So what we will do is an application of this learning model. So can I continue, or should I give some time for you to copy? I continue? Well, I'm asking because I will need a new one. So we'll have the example 4.4.5, which is a specific application of this learning model where you have a problem with a clerk, okay? So you're trying to measure the rate at which a postal clerk can sort mail. Look, for the people who are leaving early, just don't make noise. One thing that really bothers me, I don't care if you leave. Frankly, I don't care if you come. What I care is that you make so much noise that people who are actually standing in the class cannot hear, and then they come after the class and they ask me, what did you say in the last 2 minutes? That's all what I care. You are an adult, you can do whatever you want, you have free will, so just don't make noise if you leave, okay? So, after 3 months, the average clerk sorts and then we're given the specific shape of Q, 700 minus 400 E minus 0.5T, so this is the actual form of Q. And Q represents the number of letters per hour. So we're measuring the efficiency of this clerk. So we have 3 questions. How many letters can a new employee sort per hour initially? This is a specification that is not indicated in the book, but I mean, in a way, it's common sense from the context, but this might be important. The second is, how many letters can a clerk with 6 months of experience sort per hour? The third one is approximately how many letters will the average clerk ultimately, meaning that you will have to take a limit as time approaches infinity, be able to sort per hour. So, of course we won't be able to finish the problem, but we can do some posing of the problem. So, initially, what you have, if you plug in the value, is 700 minus 400 times e to the 0, so you have 300. So, the second one is that after 6 months, what you have is just to plug in, the units of time are in months, so you have 700 minus 400 e minus 0.5 times 6. So if you were to make the computation, what you have is 700 minus 400 times e to the minus 3, which is around 680 letters per hour. And the last piece of information, but we finish the exercise, is simply the limit as t approaches infinity of q of t. Well, basically you have 700. So this is kind of like the maximum efficiency that this person will be able to have. Okay, so see you next class and good luck.